Hello everyone, welcome to Discriminant Analysis lecture. In this lecture, I will describe the method of discriminant analysis, which is a model-based approach to classification. I will start by giving the background and the main principle, and then I will review an example with its algorithm. Lastly, I will mention the case with multiple classes. So this lecture will be a theory and practice class together. So discriminant analysis is a model-based approach to classification which is based on the distance of a record from each of the class means. So we are supposed to calculate the class means. So this method was used or has been used for classification long before data mining. It was used for classifying organisms into species. It was used in finance to classify loans or customer types. Discriminant analysis uses sets of measurement on different classes of records to classify new records into one of those classes, which is the essence of classification. Okay, take a look at this example. The goal of this example is to classify each customer into one of two categories, either default or not default. In this Excel sheet, there are three columns. The first column is the classification of the customer that we are going to predict. The second column gives the mortgage balance, and the third column gives the income of the customer in thousands of dollars. We have one outcome to predict, which is column A, and then we have two predictors, which is balance and income. Now let me illustrate this data on a scatter plot using a Python code. Okay, so let me start with the libraries first. These are the libraries that I will be using, and then let me import the data. This is the data sheet I showed you. I imported data to Python. Now let me create dummies. Okay, so this code dropped the first default column and instead it produced a dummy variable which is called default yes. Now I will show you scatter plot of default versus balance and default versus income. Okay, this chart shows the relationship between balance versus default. As you can see, the higher the balance, the higher the probability of default. So there's going to be a kind of S-shaped curve here. And then for income, there's a kind of reverse S-shaped here. So the higher the income, the higher the probability of not default. So the S-shape is going to be something like this here, but it's going to be like that there. Okay, so this part of the code is a little bit long. That's why I'm going to copy and paste it here, but you can find the code below the video as always. I would like to give the idea. This code basically draws a scatter plot of balance and income. So balance is on y-axis and income is on x-axis, and the green points represent the people who did not default and red points represent the people who defaulted. So this blue line is an ad hoc line, so there's no formula. I just drew it casually. It has no meaning other than just to give you an idea. So basically the whole idea of discriminant analysis is draw a line between those two classes so that I can classify each record in one of those classes. So how can we draw a line between those two groups? So basically this drawing will be based on the distance of a record from each of the class means. So I'm going to find the class means of two groups, and then depending on the record's distance to the mean, it's going to be classified whether it's going to be in the defaulted data set or non-defaulted data set. As you can see, the income of the green group seems to be larger than the red group, and similarly, the balance of red group seems to be larger than the green group. This is again the same data with two crosses in it. This cross shows the class mean of green points, so their average income and their average balance. And this cross shows the average income and average balance of the red group. Basically, this is the essence of discriminant analysis. So we are going to find the class means of both groups, and we are going to classify a record depending on its distance from those class means. So the idea once again is to classify a new record and measure its distance from the center of each class, then classify the record to the closest class. We need to measure each record's distance from the center of each class. This center is going to be called centroid. This centroid is simply a vector list of means of each predictors, and this mean is computed from all the records that belong to that class. So in my case, there are two groups, income and balance. So there are going to be mean of income and mean of balance of red group and green group. So it's going to be 2 by 2 data. Just roughly take a look at this green group. So the income of green group seems to be somewhere around $35,000, and the income of the red group seems to be somewhere around $21,000. Similarly, the balance of red group seems to be somewhere around 55. The balance of the green group seems to be a little less, maybe 54 or 53. Okay, so a popular distance metric is Euclidean distance. We use this with k-nearest neighbors method, so we can use it to measure the distance of a record from a class centroid. Basically, x1 bar is the mean of first predictor, say income. x2 bar is the mean of the second predictor, say balance. In my example, there are only x1 bar and x2 bar. But it might be the case that we might have p predictors. So the drawback of this method is sensitive to scale, so we can normalize it, and it ignores the correlation between the variables. A solution to these drawbacks is to use a measure called statistical distance. In this formula, S denotes the covariance matrix between the p variables, and S inverse is the inverse matrix of S, which is the p-dimension extension to division. When there is a single predictor, p is going to be 1, and this formula will reduce to squared z-score calculation since we subtract the mean and divide by standard deviation. So the statistical distance takes into account not only the predictor means, but also the spread of the predictor values and the correlation between the different predictors. The idea is to create classification score that reflects the distance from each class, and this is done by estimating the classification function, which are a function of statistical distances that I showed a moment ago. Let's run the Python code to see how this is performed. Okay, I'm just copying and pasting this code. This code gives me two coefficients, one for the balance and one for the income, and it also provides me an intercept, which I will show you in a moment how to use. These coefficients are basically the coefficients of the discriminant line that's going to separate two groups, basically the green group and the red group. Now let's draw the scatter line. This scatter line, this dashed orange line, basically this dashed orange line divides my data into two groups. If a record is to the right of dashed line, it's going to be classified as non-default. If it is to the left of dashed line, it's going to be classified as a default data. Okay, let me show you a little bit more in detail. So this code just takes the balance and income, and using these coefficients that we calculated a moment ago here, using these coefficients, it's going to take the balance and take the income, and default is also given. So these first columns are given. It's going to calculate a function which is either negative or positive. If the function is negative, then the prediction is going to be that this is going to be non-default data. So this is prediction is 0. If it is positive, for example, here, then it's going to be predicted as default data set. Let me illustrate this in a numerical example. Okay, here's how we are supposed to use these coefficients. The first coefficient is going to be coefficient of balance. So I have two predictors. The first is balance and second is income. So the first coefficient times the balance plus the second coefficient times the income plus the intercept, it gives me a number. If this number is less than 0, then this record is going to be classified as non-default, which is 0. If this number is higher than 0, then this is going to be classified as default, which is 1. Okay, so this is going to be my criteria. First coefficient times balance plus second coefficient times income plus the intercept. For example, let's check the first record, which has a balance of $62.39,000 and income of $42.03,000. So we substitute everything in this formula. It gives us negative 5.6. Then this number is negative. That's why I'm going to classify this record as non-default, which is 0. So that's the whole essence of discriminant analysis. If this was higher than 0, then that's going to be classified as default. Before finishing, let's overview our data set once again. We had balance in the first column, we had income in the second column, and in the third column we have the default dummy, which is either 0 or 1. And we are going to use discriminant analysis to create this function. If this function is negative, then we are going to predict that the customer is going to be in 0 class, which is non-default. If this data is positive, we are going to predict that this customer is going to be in the second group, which is default data set, which is 1. Okay, lastly, let's measure the classification report. As you can see, the precision of my model is quite high. The weighted average is 92% and macro average is 87%. One last thing that I would like to do is I'm going to copy and paste our logistic regression code from our previous class, because as you might remember, logistic regression was also classifying between zeros and ones. So I'm going to copy this code from my previous class and then compare it with discriminant analysis. So let's write here comparison with logistic regression. So this is what logistic regression does. It's going to use income and balance once again. It's going to come up with a prediction. Let's define our outcome and a predictor matrix. So this is X. And so this is going to be my predicted values for logistic regression. Also, I am also drawing the line chart. So the red points are my predicted values and blue points are my actual values. So this is for income and this is for balance. Now let's take a look at our prediction. So this is going to be the prediction for my logistic regression data set. Balance, income, default, yes. These are my probabilities of default and these are the predicted values. So the last column is going to be the column that I'm going to compare with discriminant analysis, and let's do the same thing here, and then this is going to show me the classification of logistic regression. Okay, as you can see, the values are quite similar. So this is 92% and 87%. Logistic regression also produced same performance with discriminant analysis. One last question before we finish is that what if we have more than 2 classes? Well, in this case, the model produces more than one probability. In our case, we had only one probability. So if the probability is higher than the cutoff, then it's going to be classified in one class. So if we have more than 2 classes, then the model produces, let's say, 3 probabilities. So let's say there are 3 categories here. The probability, the propensity of the first category, the propensity of the second category, and the propensity of the last category. Every single record is going to have more than one propensity. In this case, 3 propensities. For example, take a look at the fourth record. The fourth record has 3 propensities. Whichever propensity is higher, then that record is going to belong that category. For example, for the fourth record, the second propensity of no injury is the highest, then the fourth record is going to be classified as no injury case. Well, that's all about today's class. I hope you enjoyed this video and hope to see you in the next videos.